Okay, well, maybe I can just introduce our next speaker, even though he can't hear me at the moment. But his name is Mikael Rasola. He's a project manager at Wallenius Marine. And he's going to talk to us today about a very interesting project that they have, looking at sailing ships. So that's, I think, something we're hearing more about in the future. So prelude to sailing ships, collection of wind data using LIDAR on operational shipping. And so we'll see if we have Mikael with us now.
Yeah, I'm with you.
Oh, great.
Can you hear me?
Excellent. So I introduced you, Mikael. I'm not sure you heard it, but I did. And so the floor is yours.
Thank you for the introduction. I did hear you.
Great.
Yes. So I'm the project manager working on a research project at Wallenius Marine to support our development of what we believe will be a disruptive technology change in shipping. And we do this project with the support of the Swedish Transport Administration, which we are very happy for, together with our excellent partners, the Royal Institute of Technology in Stockholm and SSPA in Gothenburg. So Wallenius has a very ambitious plan. We want to set sail again. And we want to set sail now. And some of you may have seen Ocean Bird, the boat in the background. But just to set the scene a little bit, I'll show you a short movie here to get us started. And I hope. So in order for that to become reality, we have been working very hard for a long time now together with our partners. We've been working in various different areas, of course, with the traditional naval architecture topics, ship design, but also quite a big package in logistics and risk, which we think that this will be disruptive in the service chain. So together, especially with SSPA, we have worked very hard on logistics topics to make this happen. We think that we need to have a very holistic approach if we want to see this in the water. But today I would like to focus on a very small but important part of this project. And that is really the core of Ocean Bird. And that is her wings and their ability to generate fossil-free propulsive power. So it will be a little bit technical here, but I hope you follow me. So if lift generation in theory is quite simple. So if we have a room where the wind is blowing from one direction in the entire room, and we put the wing in that room and angle it slightly towards the wind, we generate lift. If we have a uniform inflow of wind, it's quite easy to determine the size of that lifting force and the cost in terms of drag. And this lifting force is exactly what propels Ocean Bird through the water. So this is important. In theory, things are usually simple. In reality, they are not, is my experience. What we're looking at is a ship that is around 200 meters in length. The wings stretches more than 100 meters from the ocean surface up in the air. And that is exactly one of the things that makes this problem of determining the actual power we get from these wings slightly more of a challenge compared to the sort of theoretical case. Many of you probably know that there's an atmospheric boundary layer. So usually the common understanding is that the wind is blowing, the wind speed is varying with height. So close to the ocean surface, the wind speed is lower compared to the wind speed at higher altitudes. This is common understanding. There are simple models that describe this phenomena. But we thought that this is so important for the performance and safety of Oceanbird that we needed to understand this better. We needed to know more. And we looked into trying to find open data on this boundary layer. For example, could it look like this? Was it more flat? Could the boundary layer even be reversed so that the wind speed is actually higher at the bottom, close to the surface than higher up, so to say? Or could there be a situation which looks completely different from what we think? But open data was scarce, so we thought, well, we have access to quite a large number of ships going all over the oceans. So why not try to collect this data ourselves? And that's exactly what we did. The project needed information on wind speed variations as a function of altitude, and also the wind veer. And by veer, I mean how the wind twists with altitude, and up to 200 meters above the ship. And we need this as a basis for performance evaluation, wing and hull aerodynamic design, and also for actually mechanical design of the wings. So we designed a measurement setup centered around a LIDAR. That's a light detection and ranging equipment. Basically what this equipment does, it sends a laser beam up into the sky. That laser beam has the ability to measure the wind speed and direction in 3 dimensions at a number of predetermined heights. So in our case, we're interested in the region between 0 and 200 meters above the ship. We developed an autonomous logging system around this LIDAR. So we combined it with an inertial measurement unit to compensate for the ship motions. We complemented it with a high frequency ultrasonic anemometer and provided the LIDAR with communication equipment to be able to send the data home to us wherever in the world the ship may be. We installed the LIDAR on the vessel Figaro in the port of Gothenburg. And the installation looks something like this. This is a picture taken from somewhere in the English Channel, I think. Here we have the LIDAR setup, and here we have the ultrasonic anemometer. And a fun fact here is that this blue container, I'm not sure if you see it, that actually contains wind washing fluid. So on top of this, there's a wind washer to make sure that the LIDAR has a clear view of the sky. So we sent this ship out, and I'll just give you some examples of what we collected here from 2 North Atlantic crossings. These crossings were done in November, December in 2019. It's about 40 days of data and 14 days over open oceans. All the data I'm talking about here is averaged over 10 minutes. So what did we see? Well, this is an example of one day in December in the middle of Atlantic. What we have in this graph here, each line here is one of these 10-minute averages. Here we have normalized wind speed. So I've normalized the wind speed with the wind speed at 200 meters height. So if we go down here, we see that the wind speed actually decreases as expected when we come closer to the ocean surface down here. But what we also see is a very interesting phenomenon happening around the ship hull. So the ship hull affects the inflow substantially, quite high above the ship, up to 30-40 meters above the ship hull. And we also see that we have a very large variation in how these profiles look, even within one day. So one way to aggregate this data is to compare it with existing models. And I don't want to go into details, but this is a prevailing model to describe the change in wind speed as a function of altitude. And it's basically this parameter alpha here that determines how the slope of these profiles look. So we fitted our data to this model using the highest 7 highest altitudes to avoid including the effects of the hull, to assess how did our measurements compare to well, sort of standard models for this boundary layer. And what we saw was interesting. First of all, we see that the exponent here is actually negative in some cases, which means that the wind speed is higher closer to the surface than higher up in the atmosphere, which was a little bit unexpected. We can also see that the majority of the cases that we looked at, we have an exponent that is fairly close to zero, meaning that we have a very flat profile compared to, for example, this black dash line, which is the ITTC standard value, very, very commonly used, which predicts a much more varying boundary layer. So that was very, very interesting. What we were then able to do with this data is also combine it with these measurements with simulations. So we used computational fluid dynamics together with our partner SSPA to derive correction factors for the near hull region, to understand and validate simulation tools for wing-hull interaction and improve our performance prediction capabilities. What this combination of tools also allowed us to do was to make some draw some very valuable conclusions on the actual design of Oceanbird, which is, from Wallenius Marine point of view, extremely important output from the research project, of course. So just to conclude a little bit, we had a very successful snapshot, we believe, of the wind conditions on the North Atlantic crossing. We gained some very valuable information on the flow conditions in the near hull region. We saw that the boundary layer profiles, for example, is flatter than expected, which from our point of view is quite nice because we don't have to deal with a twisting wind. We saw a very low level of veer, so the wind twist with altitude was also very low, which is, from our point of view, again, quite nice. We showed that we can use CFD to expand the value of the measured data set and gain valuable insight into wing and hull design. And this is still ongoing work. So we have tons of data still to analyze, for example, in near shore and in-port conditions, which are other very important aspects of this. And we're actually planning now to go on for further measurement campaigns. Now, the Corona situation has been a little bit of a challenge for us with this, but now it seems that we shall be able to get out on the oceans again this autumn. So thanks for your attention, and I'll be happy to answer any questions that you have.
Great. Thank you very much, Mikael. It's very exciting to hear, I think, how we can use ships as a platform to collect data. And I know that your company, that you don't only collect wind data, you also collect other types of data, I think. I know you're not working with that, but I find that very interesting as well. And so my first question to you will be, how do you see ships as a platform of collecting data in the future? Do you think there is a untapped potential here, or what's your view on that?
I think there is an untapped potential in dealing with the data. We've been logging data from our ships for the past decade, more data than we can. We cannot always handle the amount of data that we log, and that concerns motions, weather data. So I think that for sure is a huge potential but we have to make the systems more autonomous, and that's not my area of work in Wallenius, but it's something that we work quite hard with, really trying to harvest the value of that data.
Right. And so is the data open for anyone to use, including the wind data that you were talking about? Because I guess that's part of it. We have all this data that we're generating and that Robin was talking about earlier as well. But if there's not access to the data, how can we use it in a good way? What's your view on that?
I mean, it depends on what data you mean, of course. Some of the data we collect is performance data, which is sort of business sensitive for us, and that, of course, we can't share in every way. But the data on the meteorological data now, of course, that is something that we're happy to discuss cooperations with interested parties on that, for sure.
Because I find it exciting, which I think you've done in Ocean Data Factory as well, Robin, where you mix all these different competences. You have people that are good at modeling data, and then you have maybe the biologists that are good at knowing what's going on in the environment, and sort of mixing those competences. I think it's interesting, because I'm thinking, Mikael, you might be sitting on really interesting data, but it's just that another perspective is needed to know that it is interesting data, if you know what I mean. So
yeah, for sure.
Yeah. So that was just a comment from me. There's no questions in the chat yet, but well, yes, there is one. Okay, they're coming up. But until I have them here on my screen, Robin or Pujan, do you have questions for Mikael? If you're still with us on this link. Oh, maybe they've logged off.
Yes, I'm still here.
Okay,
I'm just wondering. Yeah, hi. Sorry for the lag. I'm hoping it's better now. Yeah, there. No, thank you, Mikael. It's super interesting presentation and fascinating to see this. I was wondering, in terms of ocean wind, the offshore wind installations, if you've been speaking with any organizations about sharing data with organizations that are implementing ocean wind.
We have not had very active discussions with that sector yet. So we had mainly discussions with different research institutes and universities with regards to this topic. But for sure, it's an interesting. I mean, they're facing somewhat similar, or probably gathering somewhat similar data for sure.
Okay. Great. Well, thank you very much for your presentations, all three of you. It was very interesting to hear. And so we've been listening to presentations on how we can use drones, how we can use ships for collecting data. And so I just want to give a heads up for the session just before lunch. After the break, we're going to talk about animals as the carriers of sensors. And so now I'm also getting some questions here. So we'll do that one for you, Mikael. How deep keel do you need to compensate for the sails?
Oh, good question.
Mm-hmm.
Actually, you don't need a keel at all. If I'm
surprising.
There's but a keel will of course increase the performance of the ship. And if it's one or several keels, that will probably be revealed in the future. But there is of course a lot of interesting stuff happening underwater for a sailing ship, as you can imagine. But it's not, as I said, you could actually even do it without the keel.
Oh, I would never have thought that. So there's more data to be collected there, I can hear. What happens under the water when we have sailing ships? So we have one more question. We'll take that as well, as we started a bit late, and then we're going to have to wrap up. The question reads like this. The wind speed profile versus, I think, height was very interesting. Do you think this should be similar, flat, out in the Atlantic like it is in the Baltic Sea? Do you already have some insight on data in these regions? Does that make sense?
No. Yeah, it makes sense. The question makes sense.
Yeah, good.
Yeah, we only have data for North Atlantic as right now, and we don't have. Well, the rig we can place on anything. That's pretty autonomous, the rig. But our ships are generally the ones we have access to is generally more open ocean than the Baltic. So right now the data is focused on that.
Yeah, and so do you have any plans to do similar things in the Baltic?
Not right now, no.
No. Okay. Good. Yeah. Great to have questions from you in the audience. Really, really great. So I encourage you to keep asking questions in the chat. It's fun to see what you're thinking about when you're sitting there watching this webinar at home or at the office, wherever you are. So thank you so much, Mikael. Thank you so much, Pujan and Robin. It was great to get those sort of quite overview presentations to lead us into this day and all the interesting topics that we're going to deal with today. So like I said, be with us for the half hour before lunch, where we're going to look at animals as the vehicles of carrying sensors would be a bit different from what we've heard now. Before that, we will also have a discussion with our opening speakers together with Nils from Divine Robots, who's just going to join us for that. But now I'm going to hand over to my colleague Torsten Linders, who is in the workshop with all the technical cool stuff. He's going to talk a little bit and show us some stuff there. Oh, I can see you. This is so much fun. I feel like I'm on telly. What I wanted to say was that if you're following the program, you see that it says coffee break. So this is sort of something you can listen to while you're brewing your coffee at home. But there will also be about 20 minutes, 15 minutes where we won't be talking at all. So, and then we reconvene at 11 o'clock with the program. So over to you, Torsten.
Thanks a lot, Jessica. It's quite correct what Jessica said. It's allowed now to take a coffee, and I will talk very briefly. I will not actually show anything, that comes later. What I want to do as I stand here in the electronics workshop is to do a very short pitch for what comes later today. And then we will return to this workshop where I will meet quite a few people and I will ask them why they feel so passionately about ocean data and the means to collect that data. We will also get a proper show and tell from the technicians who work with the equipment that you can see around me in the background. That is Luis and Olle from VOTO, the foundation Voice of the Ocean. Very much we're looking forward to that. And after that, we will actually step outside and take a look on some more experimental work, and we will do that live on the water in the marina. And finally, I would like to bring to your attention that there is actually action going on right now as we speak on the water. I have posted some information about that in the chat, and that is our special guests from the Science Club, students of the Science Club in the municipality of Lysekil. They are out on the water. They have deployed the drifter built by Science Club, and the data from that drifter has started to come in. And after the lunch, we hope that they will show a little bit about what they have done. All right. Now it's proper break.